Okay, today's lesson is 4.4, Prove Triangles Congruent by SAS and HL. So today we're clearly going to get into what SAS means and what HL means. Postulate 20. Now, whenever you're doing this on your test or quiz or notes, instead of writing postulate 20, write SAS so I know what you're talking about. When I went over your test, I had to go back and review what theorem 3.4 is, because I know what the theorem says, but I don't know what number it is. So write SAS. If you type HL, then write HL, not postulate 21. Postulate 20 stands for side, angle, side. Makes it a lot easier too. SAS, side, angle, side. You don't have to memorize what postulate number 20 is. It's just SAS. All right, if two sides of one triangle are congruent to two sides and the included angle of a second triangle. Now that's the important part. You have to have two sides and the included angle. That is the angle between the sides. Okay? That's what makes it included. Now, people always say, well, it's still in between the sides. So if I have a triangle here, like this, right? And I know this is congruent to another triangle, and that's congruent to another triangle. Then I need to angle in between those two. It has to touch both sides of the triangle. People have said in the past, well, if I have this, I have this, and this, well, then this angle is still in between, so I can go around and come to this. That's not the way it works. It has to be touching both sides to be the included angle. Anyways, if the two sides of one congruent triangle are congruent to two sides and the included angle of a second triangle, then the two triangles are congruent. And here we have a picture of what that looks like. So triangle RST is congruent to UVW. RST is congruent to UVW. Because we have this side this angle and this side congruent to this side, this angle, and this side. So that matches up with that, and you can tell by the two markings, this matches up with this. You can tell because it's only one hoop or arc going through it, and this matches up with this. You can tell because it's only one line. Now we get to write proofs again. I know you guys are excited for that. I'm going to bring this in a little bit so that it might be a little harder for you to see, but it's going to give you time to write down at least all the statements. So go ahead and write the statements down. You don't want to pause the video so that you can do that. Get them all down. You're not going to be rushed. Okay. If we look at our statements, the first one is BC is congruent to DA. Now, how do we know that? Well, it says it up here under given. So your reason would be given. How do we know BC is parallel to AD? Well, that is also given to us. And it says angle BCA is congruent to angle DAC. So whenever it tells me that, I mark it down. I have to come up with a reason for it. I need to know that BCA is congruent to DAC. If I look at that, we have two parallel lines, BC and AD, and it's being cut by a transversal. So this is alternate interior angles. All you have to do is say AIA. That's how you know. Or you could say alt int. Either one is fine. But I know that alternate interior angles are congruent. I told you that stuff was important. Then AC is congruent to CA. So this line is congruent to this line. Now, how do we know that this one line is congruent to itself? That would be the reflexive property. So we have a side congruent to this side, this angle congruent to this angle, and this side congruent to itself. So I see side, angle, side. And the angle is the included angle. So how do I know the two triangles are congruent? By SAS. And that's all you need for that one. Now I'm going to have you do the statements and the reasons. In the diagram, QS and RP pass through the center M of the circle. So since it's the center of the circle, it's the midpoint of the circle. What can you conclude about triangle MRS and triangle MPQ? Well, the first thing that I know is the only piece of information I'm given. M is the center. And I know that because it's given. There should be a 1 there. So, reason number 1, even though it's the second thing I wrote. Number 2, then MS is congruent to MQ. Now, how do we know that this half is equal to this half? What's the definition of midpoint? If this is in the center, it's the midpoint of this segment, which means I can cut the segment perfectly in two. By the same token, we can do the same thing with RM and MP. So we can say RM is congruent to PM, and the reason for that one, definition of midpoint. See, this side is still, or these are still touching the circle. We can say, so I have a side and a side. There's no way to tell that this side is congruent to this side. So lets me know I need to look for an included angle at this point, because I have a side and a side, which means it's got to be an angle inside of it. It's got to be included, so it's got to touch both sides. So now I have side, angle, side. That's congruent to side, angle, side. So it's kind of your giveaway for step 5, reason. SAS. But how do we know that angle SMR, let's do MRS. It's the same thing. No, it's not. SMR is congruent to angle QMP. The only way we know that is vertical angles. The vertical angles are straight across from each other. So it would be vertical angles are congruent. If you just wrote vertical angles, I would give you credit. Now we have side angle side, so it's the last statement. Oops. Struggling today. MRS is congruent to triangle MPQ. By side angle side. Okay, this takes us to the hypotenuse leg. Hypotenuse leg shows in this triangle that you have the hypotenuse. It is always the longest side here, and these are both considered legs. One of the things to know for a hypotenuse leg is that this has to be 90 degrees. If you do not have a 190-degree angle in your triangle, then you cannot use hypotenuse leg. Only use for right triangles. Remember, if it ain't right, you did it wrong. See, if it ain't a right triangle, you did it wrong. All right. Legs of a right triangle always form the right angle. The hypotenuse is always opposite the right angle. And here's our theorem for it. Again, don't learn the theorem number. Write HL. That's all you have to write. Theorem 4.5, hypotenuse leg congruence theorem. If the hypotenuse and a leg of a right triangle, remember, if it ain't right, you did it wrong, are congruent to the hypotenuse and a leg of a second right triangle, then the two triangles are congruent. Okay, we're going to use the hypotenuse leg congruence theorem. So I'm going to pause the video for the last one because I know I flew through that, so you can write it all down. And then you're going to have to pause the video for this as we go through it. By the way, this is a pretty important example. On the side here, you can see that they decided to write HL. That's whenever they found the hypotenuse in the leg. Okay, AC is congruent to EC. How do we know that? It's given. AB is perpendicular to BD, and ED is perpendicular to BD. And it's also given. Then we know angle B and angle D are right angles. Okay, now that we know that they're right angles, we know that hypotenuse leg is a possibility. Triangle ABC and triangle EDC. ABC and EDC are right triangles. And that's by definition of a right triangle. A right triangle has to have a right angle in it. It's mind-blowing. AC is a bisector of BD. What does a bisector mean? Well, first, that's given. It says it up here. Then for the next one, what does a bisector mean? It means that it cuts it perfectly in half through the midpoint. So then you know BC is congruent to CD or DC. And triangle ABC is congruent to triangle EDC. You know that because of HL. That's all you need. So this is an example of how hypotenuse leg is used. Okay, you're going to need a worksheet on this. As always, this is going to be your typical three worksheets. Try to do it without looking at your notes. See if you can figure out exactly how it works. All right, good luck. Taping.